Hi everyone, and welcome to the final seminar of the COMBAT project, which is short for Compartment Explosion Induced by Batteries. And the outline of the presentation will be that we will start with an introduction of the research team, the founding agencies, and the advisory board. And then we will go through a background and present some of the results from the literature study part 1. Then we will have a short coffee break and come back to a presentation where we present the results from the literature study part 2. And in the end, there will be some time for discussions and questions. And then we will finish everything with some closing words. So the research team of this project works at RISE, which is the Research Institute of Sweden. And we are over 3,300 employees that work all around in Sweden. And also some parts are located in Norway. But the research team of this project works at the Department of Fire and Safety, which is located in Borås. And here we have been doing fire testing since the 50s, and we can test anything from doors to full vehicles. And last year we opened our brand new battery lab, which you can see in the picture here below. So who am I? And I'm Maria Quant. I'm the project leader of this project, and I have worked as a researcher at RISE for about 2.5 years. And before that, I did a PhD in chemistry at Chalmers University of Technology. And on the team, we also have Oskar Grönlund, who has a fire engineer background and have been working for RISE for a little bit more than 2 years now. And then we have a senior researcher, Johan Andersson, who is the expert in modeling and explosions and simulations. And finally, Petra Andersson is also a senior researcher who has been working with fire dynamics and similar for over 30 years. And before we start, I will of course like to thank the founding agencies and the advisory board. And the founding agencies are Stiftelsen Sveriges Sjömanhus and the insurance company If. And in the advisory board, we had quite a broad group with people with different backgrounds. So fire consultants, the civil contingency agency, rescue services, insurance companies, battery manufacturers, and also universities. So thank you very much for your contributions to this project. Yes, so let's start with some background. And we all know that there is an ongoing electrification in the society, and we now see batteries more or less everywhere in our phones, in our computers. And the past decades, there have been a great increase in the electric transportations, especially in road transportations. But lately, there have also been an increase in the maritime industry. And as illustrated in this figure, we can see that the installed battery capacity in ships in operation and on order are increasing. And the application is mostly for hybrid or plug-in hybrid propulsion, but there is also fully electric ships on the market. And there are many different battery technologies with different working principles, and their properties and safety aspects varies. And batteries can be divided into 2 categories, so primary and secondary, so the rechargeable and the not rechargeable batteries. And when we speak about the road or sea transportation, of course, we are interested in the rechargeable batteries. And there are many technologies. There are older ones, such as lead acid, nickel cadmium, nickel metal hydride, And then we have the lithium-ion batteries and also newer technologies, sodium-ion batteries, solid-state batteries, and flow batteries. But this project is all about lithium-ion batteries that are the dominating type on the market today. And lithium-ion batteries are also a big family of batteries that comes in different shapes, properties, and with different safety risks. And here is a table of the most commonly used lithium-ion batteries. We have NMC, LFP, LFMP, LMO, NCA, LCO, and LTO. And they have different cathode and also sometimes anode material and different properties such as the energy density. And what technology is preferred depends, of course, on the application. And in road transportation, the NMC batteries are common because they have a high energy density. In LFP, stationary energy storage system, LFP cells are very common to use since energy density is not so important as with transportation. And in the graph here to the right, we can see cell chemistry by average installed battery capacity in ships. And here we can also see that the most commonly used chemistries are NMC, LFP, followed by LTO. But one thing that all lithium-ion batteries have in common is that they can enter a state called thermal runaway. And thermal runaway can be triggered from different parameters, such as short circuits, internal or external, from overcharge, from over discharge, and from external heating, and also from deformation and penetration. So what happens inside the cell is that the temperature slowly starts to increase, which will trigger exothermic reaction to take place, which will release even more heat and trigger more reaction until it reaches a state where the temperature increase is just out of control and cannot be stopped. And what happens in the cell is that gases start being produced, so the cell will swell until it vents, or the casing will rupture or explode, and then we can get a fire or even a gas explosion. And in a battery system, we usually have more than one cell. So if thermal runaway starts in one cell, it is a risk that it can propagate or spread throughout the whole battery system. And that's when we can see these severe accidents. So flammable gases from batteries in thermal runaway that are not ignited and that can accumulate in an enclosed space is an explosion risk. And in the figures, we can see tests that we did in our labs. And in the first one, we overcharged cells in this semi-enclosed space, and it resulted in an explosion. And in the picture below, it's a cell that are being heated, and we can see that a lot of gas is being produced. And accidents involving explosions can, of course, have severe consequences. And there have been examples of accidents where explosion happened. And the first one is in MF Ytterøyingen, which is a Norwegian ferry. And there was a coolant leakage in the battery room, so that caused a fire. And firefighters came to the scene, and the same evening they reported that the fire was under control. But then the next morning they opened the door to the battery room, and then a few hours later there was an explosion. And a similar incident was from MS Brin 2021, also a ferry in Norway. And this time seawater had entered the batteries, but the firefighters had learned from the previous accident, so this time they did not open the battery room. Instead, they were purging it with nitrogen gas and ventilated out the flammable gases, so they could avoid an explosion. But this procedure was far from standard and took some time. And then you have all probably heard of the McMicken accident in Arizona 2019. There was a fire in an energy storage system, and when firefighters came to the scene, after a while they couldn't see visible flames and temperatures were decreasing, so they opened the door, oxygen came in, and again there was an explosion. And in this accident, firefighters were injured. And there was also one in China, in the Hongmen 2021, and here they had placed the battery energy storage system outside the main building. Something goes wrong and over 200,000 cells enters thermal runaway. So there's an explosion and fire in the energy storage building. But what also happens is that gases spread in an underground cable trench to the main building, where there is also an explosion. And in this accident, unfortunately, firefighters and personnel died. And last example, we see more and more of incidents in houses. And here is an example from Schönberg from this year, where a small energy storage system connected to solar panels exploded. And as you can see, there are quite some damage to this building. And we've been looking into some statistics regarding explosion risks. And in general, when it comes to battery accidents, statistics are lacking. And in most cases, the root causes are unknown. But some data have been collected. And from that, you can see that failures starting in cells and modules that causes severe accidents are rare. And in most cases, it's due to other parts, such as the balance of the system or controls of the system. And to the right, we see data collected by UL, and they looked at failure types for residential energy storage systems. So the smaller ones that you can have in your house or in your garage. And they looked at the outcome of the accident. And in 75%, there was a fire. In 6.7%, there was venting of gases, but nothing more. And in 18%, there was explosion. But it's worth mentioning that these smaller systems usually don't have safety measures such as extinguishing systems or ventilation. But to conclude, there is an explosion risk with batteries that we have to take serious. So the goal of the Combat project was to investigate how the explosion risk is affected by the battery parameters, the total volume of flammable gas that can be released during thermal runaway, and how this is influenced by battery chemistry, state of charge, and how thermal runaway also is initiated. The goal was also to investigate the possibility of reducing the explosion risk through ventilation and how the explosion risk is affected by different extinguishing systems, such as inert gas system. And then we also looked at simulations and modeling tools for batteries and ventilation, and also the effect of air exchange on flammable gases in different geometries and situations. And the scope of the project is that this is a preliminary study, which will result then in the literature study. So we will do no experiments and also no modeling will be carried out. But we are hoping to do that very soon in a future upcoming project. And the project will also focus on lithium-ion batteries with NMC and LFP chemistries. Yes, so let's start with the results from the literature study part 1. So we looked into battery explosion hazards, and for evaluating risk, the following parameters are important. So it's the amount of gas produced, the lower flammability limit, the laminar burning velocity or laminar flame speed, also the explosion pressure and the rate of the pressure increase. And the literature studies summarize cell and battery system properties that can influence these factors. And the focus will be on the gas composition and the gas generation for the most common cathode chemistries, so the NMC and the LFP chemistry. And let's start with the amount of the produced gases and what parameters that can affect that. So first of all, it's the system design. And in general, a larger cell will produce more gases upon thermal runaway than a smaller cell. And then the extent of thermal propagation, so how much the thermal event can spread from cell to cell or module to module, will of course influence the total gas volume and also the heat produced during the event. And if a cell goes into thermal runaway, it will most likely also be internally short circuit, and a short circuit that will also most likely short circuit the cells that are connected in parallel with a failing cell. So that means that a battery system with few small cells in parallel will have a lower risk of releasing a large amount of gases at once. So system design is important. And then, of course, also the cell chemistry can influence the amount of produced gases. And for most battery chemistries, the normalized gas volume generally ranges within 1 to 3 liter per ampere hour. And that is an average of around 600 liter per kilowatt hour. And in general, there is a large spread in the collected data in the literature, but it shows that NMC cells produces more gases than LFP cells. And if we look at the figure to the left, we can see the median production of gases from LFP and NMC cells in different and test environments. So in air, where oxygen is present, or in an inert environment, such as nitrogen or argon. And the median volumes for NMC were 570 liter per kilowatt hour in inert environment and 519 liter per kilowatt hour in air. And the median volume for LFP were 370 liter per kilowatt hour in inert environment and 126 liter per kilowatt hour in air. And also there are different types of NMC chemistries, and higher nickel content in the NMC cells will result in higher energy density, but also a larger production of gases. So cell chemistry will influence the amount of produced gases, and so will the cell format. And some studies have shown that pouch cells and prismatic cell formats produces more gases than cylindrical cells. But with that said, most reports in the literature are from tests on cylindrical cells. So we need more research and data regarding this. And the state of charge, a higher SOC results in a greater volume of gas and at a higher gas release rate. This is explained by a stronger reactivity of the active material and a lower thermal stability at higher SOC. And the gas generation rate has also been found to be proportional to the thermal runaway temperature increase rate. And the cell capacity, the total volume of the battery event gas that are produced during thermal runaway show a linear trend with the increasing capacity. So that means that the normalized battery event gas will show no increasing trends based on increased capacity. But keep in mind that the larger cell can produce more gases. And then we looked into the gas composition, which is another important factor when evaluating explosion risks. And the gas compositions in the battery event gas from LFP and NMC cell contain mainly hydrogen gas, carbon dioxide, carbon monoxide, and also a variety of hydrocarbons. And carbon monoxide and hydrogen gas and hydrocarbons will decrease the lower flammability limit, versus carbon dioxide will increase the lower flammability limit. And the relative amount of these compounds will depend on the degree of chemical processes inside the cell, and therefore also a range of battery parameters will affect the gas composition, which I will soon come into. And the specific gas compositions will also depend on the test conditions, if we are doing it in an inert or an open environment. And of course, there are other gases being produced, but they are not in a lower concentration, so they do not affect the explosion risk so much, but they may be of concern for other reasons, such as toxicity. And some examples are hydrogen fluoride, hydrogen cyanide, hydrogen chloride, nitrogen oxides, and sulfur oxides. And the gas compositions will vary as thermal runaway goes through different stages. And to the right is a figure that illustrates what happens when the temperature is increasing in a battery during thermal runaway. So different materials will degrade and will produce different gases at different times. But what is missing in this figure is that usually in an early state of self-heating in a battery cell, boiling the electrolyte is common. So a lot of gases can be electrolyte vapor. And electrolyte vapor is not often analyzed during gas production studies of batteries. And cell chemistry will also affect the gas composition. And LFP cells have a higher thermal stability, and the vented gases are less likely to self-ignite than for NMC cells in an open test environment. And in the picture above, we have an LFP cell that are heated up. And as you can see, gases are produced, but they are not igniting. And in the lower picture, there is another cell type where the gases have ignited. So vent gases from LFC cells results in a lower flammability limit, larger explosion over pressure, higher laminar burning velocity than NMC cells. So if we just look at the composition of the vent gases, explosions hazard for the battery vent gas from LFP cells can be considered larger than for NMC cells. And also the state of charge will influence the gas compositions. And in general, an increased state of charge will increase the volume fraction of hydrogen gas and carbon monoxide, and carbon dioxide will decrease. And in the figure, we see concentrations of hydrogen gas, total hydrocarbon, carbon monoxide, and carbon dioxide at different state of charge. And here we can see a decrease in the carbon dioxide and an increase in the others. So if we just look at the composition, an increased risk of explosions, there will be an increased risk of explosion with increasing SOC. But on the other hand, the risk that the produced flammable gases remain unignited increases as a lower SOC. So this results in an increased risk of explosion compared to if the gases are ignited early. So what that means is that at 100% SOC, the composition might be more likely to be an explosion mixture, but they are also more likely to catch fire. And if they are already on fire, they will not possess any explosion risk, but there will of course be other problems. So finally, before we have a little break, we also looked into aged cells, and are aged cells a greater hazards? And speaking about aged cells, there are different agings. We have the calendar aging, so how many years old are the batteries, and also how many times has it been cycled, so charged and discharged. And aged cells can influence safety, and according to the existing literature, the thermal runaway behavior during the aging process depends on the degradation history and mechanism. And in one study, we saw that gas explosion upon abuse was not affected by the cycling aged. And there was also conflicting results regarding the thermal stability of aged cells. In some studies, they obtained an decrease, and in others, an increase was observed. And also the composition of gases formed in aged cells has not been investigated to any significant extent. So it's not clear, and we need more research in this area. Yes, so now it's time for a break, and we will be back soon with the literature study part 2.
So moving over to the results from literature study part 2, and let's begin with controlling explosion hazards with ventilation. So as stated in the NFPA 855, explosion control for BESS should be provided either by deflagration panels or by combustible gas concentration reduction. And this is done by maintaining a flammable gas concentration below 25% of LFL. And it's a widely used method in fire protection engineering. It protects everything from restaurants to industries from explosion due to gas leakage. And it typically keeps the gas concentration below 25% of LFL in order to keep a margin to the explosion limit. The ventilation is either activated by signals from a gas sensor, or in this case a BMS, or it could be continuously on with an airflow enough to handle a leak of expected rate and volume. But what is the expected leak or expected rate and volume when speaking of lithium-ion batteries in thermal runaway? As you know, the produced gas volume, the rate, and the composition is depending on many parameters such as capacity, trigger method, cell chemistry. So the expected volume and rate of the gases produced can be very hard to predict. And additionally, should you design the ventilation system to handle the gases from one single cell in thermal runaway simultaneously, or should the ventilation system be able to handle the whole system of cells in thermal runaway simultaneously? This is tricky questions, but there is some guidance in the literature that I will go through. So DNV proposed a battery vent gas formula based on CFD results. And instead of strictly focusing on keeping the lower concentration below 25% of the lower flammability limit, the approach instead aimed to control the maximum volume of the gas cloud with ventilation, so that if it would ignite, the pressure rise would not be high enough to breach the surrounding structure. And in the case study, they chose a maritime battery room which could withstand 50 kilopascals overpressure. After that, the bulkheads would have breached. And the results showed that the common recommended airflow of 6 air changes per hour would only be able to handle a battery cell of 0.5 kilowatt hours simultaneously, which would place a significant responsibility on thermal propagation protection. And similar results was found by Kapahi and others in 2023 using the NFPA 69 method instead. So they also found that a commercial ventilation system could handle 1 or 2 single cells in thermal runaway, but more than that you would reach above LFL. But they also found that smaller local pockets with concentration above LFL always could be found near the failing module. So they concluded that the explosion prevention system can significantly reduce the risk of explosion, but not eliminate it. And the DNV concept were further developed by Electric Light project performed by RISE and together with Chalmers, funded by Lighthouse, where ventilation were divided into 3 levels. So the first level was a basic ventilation of 6 air changes per hour, which was considered enough as room ventilation if additionally each battery system encapsulation has a separate exhaust system to ventilate each single module if there were some thermal runaway to occur. But if you don't have that, then you should have a preventive ventilation, which is always running with the capacity to handle at least 1 single cell in thermal runaway simultaneously. And then the third level, which is casualty ventilation, and that should be activated once thermal runaway is detected. And it's basically the preventive ventilation that should ramp up to an increased capacity so that it can handle thermal runaway of all cells within the detected casualty unit. And the casualty unit was defined in the project as the greatest of these 3 bullet points. Either the largest unit of parallel connected cells, or the largest unit of both parallel and serial connected cells if you don't have external short circuit protection, or the unit of cells for which thermal propagation protection, either passive or active, has been proven and verified by test. So, jumping over to controlling explosion hazards with deflagration panels, as stated in an AFP 855, it's another method to fulfill the requirement of explosion control for BESS. And as you see on the picture, deflagration panels is basically hatches, in this case on top of a container structure, which opens on a predefined pressure rise. So the pressure rise within the structure doesn't reach the level where the whole structure breaches. And there's also some guidance and studies done on this. So Peng and others in 2023 performed simulations with open foam to evaluate the effect of deflagration panels from a worst case battery vent gas explosion scenario. So they found that the highest pressurized within the container were obtained with a battery vent gas concentration of around 25% within the volume. So that's what they choose to model. The deflagration panels were almost 0.4 square meters, and the results was that even with 4 panels, they still had an overpressure of 51.3 kilopascal, and 50 kilopascal is enough for rupture of container walls. With 20 panels, almost the whole ceiling, they still had a pressure of 3.3 kilopascal, which is enough to blow out container doors and harm employees or even firefighters. So you need quite big areas in order to limit the risk or the consequence from an explosion from battery vent gases. Looking at Barrowy and others, in 2022, they performed live tests based on the UL method scales, which is cell level, module level, unit level, and installation level. And their results indicated that prompt deflagration scenarios are more likely to be prevented by deflagration panels, while delayed deflagration are more likely to be prevented by mechanical ventilation. And they also found out that only the test in their series with suppression agents, in this case water and Norvec 1230, actually caused a delayed deflagration. In the test without suppression agents, deflagration occurred seconds after the thermal runaway. So a few perks with deflagration panels. They can be used in combination with gas and aerosol fire suppression systems, while mechanical ventilation cannot, since you don't want to ventilate the suppression gas or the aerosol. So mechanical ventilation can only be used in combination with water-based system or without suppression systems. Moving over to fire extinguishing systems and their impact on the explosion hazard. So an ideal fire extinguishing system for battery systems should have the ability to provide both fire or flame extinguishing, but also cooling of the battery to stop thermal runaway and prevent thermal propagation, which is not covered solely by any existing system today. But a lot of research has been conducted on fire suppression towards libs, but less has been done on inhibiting effect of different suppression medias on the battery vent gas explosions. So this study has reviewed literature targeting nitrogen gas and liquid, carbon dioxide, heptafluoropropane, Norvec 1230, water mist, sprinkler, water spray and drencher, and aerosol-based systems. So the gases suppression systems, such as nitrogen, CO2, heptafluoropropane, and Norvec 1230, all has good ability to extinguish the flames from a thermal runaway, but does not provide long-term cooling, and thereby it has limited ability to stop thermal runaway or prevent thermal propagation between cells. And as occurred in previous accidents, once the concentration of the suppression media drops due to air leaks or if someone opens a door, the accumulated battery vent gases can ignite and cause an explosion. So looking a little bit deeper on nitrogen and CO2, they both can mitigate explosion as long as the concentration is high enough. For nitrogen and CO2, it's around 25 to 35% for CO2 and 35 to 50% for nitrogen. But CO2 has generally a greater ability to reduce peak overpressures by explosion when the concentrations are dropped compared to nitrogen. Looking deeper into heptafluoropropane and Novec 1230, both can also mitigate a battery vent gas explosion, but as long as the concentration is high enough. And in these two, it's generally enough with quite much lower gas concentration, around 5%. But explosion enhancing effects has been reported for heptafluoropropane. And this has been reported in lean conditions with lower suppression concentration than subscribed. And this is mainly because it's actually flammable and can contribute in the combustion in lower concentration. And then one of the products is also HF, which is highly toxic. A bad thing with Novec 1230 is that it includes PFAS, and 3M, the big provider of this media, has reported that they will cease the production due to new PFAS legislation. Looking at water mist, which is a water-based system with a droplet diameter of less than 1,000 micrometers. It has better long-term cooling potential than previously mentioned gas medias, but struggles to reach within cells or modules to cool within, but can limit thermal propagation between modules or racks. It has potential to reduce explosion pressures and even extinguish the flame of gas explosions, as Cao and Lee showed in 2022, it can lower the peak explosion pressures by hydrogen gas explosion by over 20% and the explosion pressure rates by over 40%, so quite big numbers. But it has also been reported that turbulence induced by water mist has reported to have an enhancing effect on hydrogen and methane explosions. The turbulence effect increases when the water mist is not completely evaporated, which is affected by the droplet size. So generally, smaller droplet size has been reported to generate less turbulence. But unfortunately, we didn't find any studies that were looking specifically at the inhibiting effects or enhancing effects of water mist on specifically battery vent gas explosions. Moving over to water spray, or as it also called sprinkler or drencher in the maritime field. This is generally a water-based system with larger droplet sizes than 1,000 micrometers. So it has higher water consumption than water mist, but as with water mist, it's unlikely to reach the failed module in a total flooding design. But it can be used to protect fire spread from a battery room or container to other rooms or structures. And it has also shown effective when directly injected into a battery pack or a module. And work by Zhang and others in 2021, it was shown that water spray applied to NMC cells can increase concentration of CO, H2 and HF, while CO2 decreases. And this could potentially influence the explosion risk, as CO and H2 is highly explosive. But the fact that it also suppressed the thermal runaway and hindered propagation might be more important. And in work by Arvidsson in 2023, the effect by maritime drainage system on burning in electric vehicles versus combustion engine vehicles was evaluated. And in terms of fire control, an electric vehicle was not considered a greater challenge than a normal combustion engine vehicle. But the study did not cover explosion risk, which needs further research. And the last system I'm going to talk about is aerosol-based systems, which has similar pros and cons as with gaseous medias. For the pros, it's cheap, doesn't require piping, it has good flame extinguishment, and it's good on extinguishing other electrical fire, so you hinder the fire spread to the actual battery cells. But the cons is that it does not provide long-term cooling, it's unlikely to stop thermal runaway, and it's unlikely to stop thermal propagation between cells. So that was all from this part. Thank you.
Thank you very much. Now we'll introduce some of the aspects from modeling of explosions in the literature survey. So remembering that we have two different use cases, deflagrations and detonations, but also dispersion of gases. This is important to remember, so you use the correct software for the best case. So the softwares are usually of two different kinds, the finite volume method or the finite element method. The FDS or the CFD softwares in general are usually of the FOM because it has inherent energy conservation. This is important for fluid modeling. However, the geometry handling is more complex in these kind of softwares. Primary use case are fluid and thermal simulations, examples, Phoenix, ANSYS, FDS, and so on. FEM are usually used for mechanical modeling. It's not inherently conservative from an energy point of view. You have to check energy conservation and other conservation properties. However, it's very efficient for complex modeling of geometries. That's important to remember, or including other types of physics. We have, for example, Abacus, LS-DYNA, COMSOL, multiphysics, etc. Now we have the case of simulation of gas dispersion. Here we have usually ventilation. This can be done with most CFD softwares. We have used in many different projects Fire Dynamics Simulator, which is a common software for fire engineering. This is a type of finite volume method software. It assumes low speed, non-compressible flows. In this case, we have a car in the upper right corner. It's spread gases. This is a fire scenario, so we have fire driving the gases by buoyant forces. And we have ventilation close to the car and in the opposite corner of the garage. The other case we have here is simulation of rapid pressure increase. This case is done with OpenFOAM CFD software. And on the right, we can see a pressure wave coming from a small booth where we have pre-mixed gases. The other case is in the lower left corner. It's a simulation of an explosion of pressure vessel on a Ro-Ro deck. And we have a very fast pressure development, and this can be done with the OpenFOAM CFD software. Here, now we come to a couple of case studies. The first one is simulation of vented gases. Here is a case from OpenFOAM, but they also have used Mech2Foam. It's a freeware where you calculate the input values that you use in your CFD software. and we can see that they have mostly good matches. It's the drawback is that it's pre-mixed. The simulated flame thickness is much higher than the measured, and you can see almost that there are some variations later on in the simulation. Next case is also simulation of LIB gases, also open foam. Here they have used Cantera to compute the combustion properties that is input to the open foam. We can see the performance of the electric storage system, where they have different deflagration panels. We can also see here that they have very fast speeds, so this is out of the case for FTS use. We can see that they have some drawbacks. The pressure dependence is very dependent on the placement of the ignition source. So the pressure buildup, the velocities through the deflagration panels is also dependent on where the event started, which is important to remember. So the third case, this is an accident analysis, a simulation of explosion hazard with different gases then. So this is a very, very odd case where they try to understand how there could be an explosion in an adjacent building. You have a gas release in one building, there is a tunnel or a connection to the building next door, where the gases travel, and then there is an ignition and a pressure wave comes out. So they try to understand how this event evolved. Of course, this is then back engineering of the accident. They have no experimental data. They took the best data they could find from literatures, and they could do some simulations. They could understand it is possible for this event to happen. So now we come to the conclusions and future research needs. Conclusions. Reliability statistics regarding battery-related incidents are generally lacking. However, available data indicates that the explosion can occur in about 18%, and there are errors in batteries and/or modules only represents around 11% of the failures. The gas composition, gas volume, gas production, rate of the battery event gases have an impact on the explosion hazards. The test method and environment, the cell chemistry, cell format, state of charge, trigger method, and cell aging affect the battery event gases. LFP cells are often considered safer than NMC cells due to the generally higher thermal stability. This study shows that the battery vent gases from LFP cells contain more H2 and hydrocarbons than NMC gases, resulting in a lower flammability limit that in turn can increase the explosion risk. Some authors claim that an increased LFL might pose a larger hazard as more gas is accumulated before ignition can take place, again showing the difficulty in finding where worst case scenarios to protect against. More of the conclusions. Explosion prevention through concentration reduction by mechanical ventilation can reduce the risk of explosion in prolonged thermal runaway events if a limited number of cells are involved simultaneously. However, there is a lack of standardized design criteria of which scenarios the system should be able to handle. One suggestion is provided in the battery fire safety concept in Electric Light project, but more research and data is needed before standardization is possible. Explosion prevention by deflagration panels can reduce the consequences of an explosion by limiting the maximum overpressure buildup. Methods to determine or advise on the parameters needed for the design of such panels are lacking. No fire suppression system is available to tackle all risks associated with TR. In terms of explosion prevention, gases fire suppression agents can, to a varying degree, reduce the magnitude of explosions and temporarily reduce the risk of explosion. Water mists tend to provide long-term cooling and can, if properly designed, reduce the magnitude of explosions. If properly designed, water mist may have an enhancing effect on gas explosion. Future research need. So, further investigate the impact of different battery parameters, for example, cell chemistry, cell aging on the explosion hazard. Perform experimental tests on batteries and/or battery vent gases in environment mimicking different compartments or enclosed spaces. Further investigation on the possible inhibition effect of gas concentration reduction by mechanical ventilation in large volume, such as maritime vehicle decks and closed parking garages. Further guidance on design parameters for gas concentration reduction by mechanical ventilation in containerized BESS and battery rooms. Further evaluation of the benefits of gaseous or aerosol fire suppression system, deflagration, water-based fire suppression system, both the deflagration panels and gas concentration reduction by mechanical ventilation. Further investigate the inhibition versus enhancing effect of water mist on gas explosions with vent gas. So now we come to the end of this presentation. So I thank the funding agencies, Stiftelsen Sveriges Sjömanshus and IF. Thank you very much for the funding. And we also thank the advisory board that has come with valuable input to our work. And thank you very much for your attention. The report